my sub teachers.
Okay.
So really, you could have expressed those 2 points as totally as functions of x.
Mm-hmm.
You didn't have to say y. In fact, I'm probably not going to speak of it much that way anymore. Okay?
Okay.
Now, let's go back. Let's go to the next page. So the purpose of this page was to talk about notation, that we could say f of x rather than y. All right?
Right.
So let's go to the next page and look at that same linear function again. I'm going to draw it. It probably won't look exactly like it, but you'll remember it,
Yes.
right? Not a straight line, but you got it. This was B. This was A.
Mm-hmm.
This was x2, comma, f of x2, if you will, right? In fact, I'm gonna let it be y for now. x2, comma, y2,
Okay.
x1, comma, y1. Now, I said we could do between any 2 points, right?
Mm-hmm. Yes.
Why don't we now consider this point here, point C, which has an ordered pair of 0, comma, b. Because you remember on a linear function, that's the great, interesting thing about linear function. Any 2 points, the slope will be the same.
Okay.
All along this line, positive infinity, negative infinity, positive infinity. The slope of this line between any 2 points is a constant.
Okay.
And it's equal to m, right?
Okay. Yes.
Constant m. So why don't I just instead, let's look at point A and point C. All right?
Okay.
So we know the slope is always going to be y2 minus y1 over x2 minus x1. But in this case, x1, y1, I'm sorry, it's going to be some value minus the change in y
Mm-hmm. Changing
over the
Y.
change in x.
Okay.
That's really what it is, delta y over delta x. Well, let's do that. The change in y between A and C, put AC down here, right? AC.
Mm-hmm.
This is really A and C, right?
Yes.
The change of y between A and C is y1 minus 0. Y1 minus b. Tripping, sorry.
Okay.
Minus b, right? This is y here. This is
Mm-hmm.
y here. On the bottom, it's going to be x minus 0. So m equals y1 minus b over x minus 0, correct?
Yes. It's a quick question, Deacon Wilson.
Yes.
How is it y1 minus b? Like, where did the b come from?
All right. B is your y component to
Mm-hmm.
C.
The x-intercept, right?
Yes.
Okay.
The y-intercept. So the y-intercept is the point where x is 0. So it is 0. But what
Okay.
is y? What is y at that point? B.
B, right.
It's the y-intercept.
Oh, okay.
So it's kind of weird because, again, calculus gets weird. So I'm only looking at these 2 points. It doesn't matter. I'm getting the same m, right?
Mm-hmm.
It's just going to be represented differently. And you can see that difference is all the difference in the world. So anyway,
Right.
you go ahead and you simplify this. You get m equals y1 minus b over x, right?
Mm-hmm.
Cross multiplying, what do we get? Hold on, got my Serbia match description here. Okay. You get mx, right?
Mm-hmm.
Is equal to what?
y1 minus
y1 minus b.
Uh-huh.
Or mx,
Yes.
it's actually, that's right. It's x1 actually, but that's fine. I'm getting ahead of myself. Remember, it's x1 here. It's
Okay.
x value at point A, it's x1. But you can see in a minute, I'm going to describe to you what's happening. Plus b equals y, or y equals mx1 plus b.
Let's
Now,
see. And that's back to the
that's
point.
right. So what is this telling us? At any, it's confirming, first of all,
Mm-hmm.
if you take any legitimate y value and any x value, it's going to work. It
Right.
doesn't matter which 2 points. We pick 2 points, go get the same thing. I just moved it here to find out what b was, to what it was a little more clearly. So here it's
Ah.
always going to be y equals mx plus b. Now, it doesn't seem too remarkable, but
Mhm.
again, all we did, think about what we did. All we did was apply
Mhm.
the fact that the slope is the same anywhere and the slope equation is the same everywhere.
Okay.
It's always the same. Okay?
Okay.
The problem comes in, and I'll get back to this in a minute, when we have a quadratic, say, or another function,
Mhm.
we're trying to find out how it's changing, we have to use some kind of a line to help us.
Mhm.
Wait till you see how this works out. All right. So it's like we're telling a little story here. All right, so we know that y equals mx plus b.
Mhm.
And the cool thing about it is that it's true everywhere on the line. Now watch this. It goes back to the definition of a slope. So I'm going to the next page. So as we
Okay.
said before, the slope was f of x2 minus f of x1, oops, all over delta x.
Mhm.
And delta x really is x2 minus x1. Let's look at that graphically.
Mhm.
Can't draw a straight line here. Let's look at this graphically. Oops. I have to have my writing tool. Oops. There we go. So in your mind, what you see is a straight line.
Mhm.
It's x2, y2, right?
Yes.
And x1,
And then y.
y1. But let's see, let's challenge the way you see it. So this is x1, up to here is x1, from 0 to
Mhm.
and up to here is x2, right?
Yes. Mhm.
So there's been so x2 minus x1 is this area in here, really. It's really in here we're looking at.
Right.
X2 minus x1. It's the amount of change between them. Boy, I have a lot more to say about that, man. In fact, I'm whipping on you now. I think you're ready.
Okay.
So I really could, if I wanted to, if I really wanted to be particular here, I could say, you say delta x is, like I said, it's x2 minus x1. But look what happens if you say delta x is x2 minus x1, Roderick. I got you now, because that means if we add x1 to both sides,
Mhm.
that means x1, write this down, plus delta x is equal to x2.
Okay. What? Okay. Let's see.
So really, this y2 is f of x1 plus delta
Mhm.
x. And this one's just f of x1.
Okay. Let's see. That is
So I'm gonna run through this again. I'm gonna run through this page
okay.
again. Okay.
Okay.
And for people who are watching the video, we said the other page back that that's really the slope. That's nothing new for you. It's just you're used to seeing y2 minus y1 over x2 minus x1. That's
Mhm.
the thing. But in the calculus, you have to look at it a little bit differently.
Okay.
You got to look at x2 a bit differently, because x2 is really x1 plus some distance you're moving here.
Mhm.
That distance is delta x.
Mm.
Boy, to me, and I haven't seen this in books too much, to me,
Yeah.
getting to this point, like it only took us a few minutes, using what we know so far, is the key to understanding why, not only what a derivative is, why we have derivatives, and how we get them.
Okay.
Because that's the theme of the first month of your class. Unless is it AP calculus?
This one is just regular. My split
Okay.
is on for AP.
So
Yeah.
he probably, what I just covered there is going to
Mhm.
take him a week to cover.
Oh my goodness.
But I boiled it down. I just boiled
Yeah,
it
for
down.
sure.
So because he's going to expect you to understand what the definition of a derivative is. And boy, I'm telling you, I know you would expect it look a lot like this, wouldn't you? And you're
Absolutely.
right, it's going to look a lot like that, even though it's a curve. But wait till you see why it's going to look like that. There's a
Okay.
reason why it goes back to a linear function
Mm.
with a little twist, you'll see. So really, this is the drawing I like people to have in their mind. So really, we relabel everything the quote right way,
Mm-hmm.
the right way. What I really should say, I'm gonna write it very clearly. Up here is x2, comma, f of x1 plus delta x, whatever that number is. And down
Mm-hmm.
here is just x1, comma, f of x1. And if you do that, then the slope is right here. What is that slope? The final slope, m,
Mm-hmm.
is equal to f of x1 plus delta x, right? That's
Mm-hmm.
f of x2, isn't it? Minus f of x1 all over delta x. This is another way you could have done the derivative of a linear function.
Okay.
Now you might wonder, well, why are we putting the delta x in? We're coming to that. We're getting to that. So I could have said, hey, look, walk this distance, then walk the delta x. You actually have done that before. Remember the homework problems where they would give you a point like here,
Mm-hmm.
count 2 over and then 1 up.
Yes.
When you were going 2 over, I'm sorry, I did it wrong. I always do it wrong. You would go up and then over here. When you
Right.
moved over here, that was delta x. You just didn't realize it. So it's never talked about. Then you can predict all of them the same way.
And that's just basically the change on the x-axis.
Yes, we always focused on the y, didn't we?
For sure. That's all they focus on.
I know, but it's really all about the x-axis. You'll quickly get that understanding. But
Okay.
that's how I wrote these points. F of x. First, I wrote them as I got you sold on this,
Mm-hmm.
right?
Yes.
And I said, well, this is really x1 plus delta x. Then I got you here. All very logically with linear functions.
Right.
With the idea of y equals mx plus b, it made sense. Slope is the same everywhere. You can predict the slope. Now, the teacher may give you problems with this, but I don't think they will. I think they'll just they'll give you problems to take home reviewing things like the following. Let's take a pause and do some hands-on. Let's suppose that point A, comma, A is 3, comma 5, that's the point. And let's suppose the slope is 3/5. And the question is, what is f of x? Okay, let's work it.
Okay.
The first thing you do is you write down, let's make it interesting. What is f of x in point slope form and standard form?
Okay.
That's what he's going to give you, that they're probably going to give you to do for homework. So let's do it. First, you write down, see, back in pre-calc and algebra 2, you use this crazy thing like y2 minus y1 equals m times x2. You don't do that here.
All right.
Now that's advanced algebra, but it's considered baby. All right, here we go. You write what you know. What do you know? You know that y equals mx plus b, right?
Oh, yeah, for the point slope. Yeah.
And we're given the slope is 3/5. So the first thing is you write what you know. You know, y equals 3/5 x plus b. Now you have to find b. And what do you use to find b? Using xy. And you have xy right here. So step 1 was you write down what you know, and you'll find out quickly, hey, I don't know b, right? So how do you find b? You use this point here and solve for B. And you come
Okay.
back here, you can plug in for B. So here we go.
Right.
Step 3, here we go. We put in the points for X and Y.
Right.
Is
So
it
it would
5
be
equal, wait, I'm sorry.
5 = 3/5 times 3
Yep.
plus B.
Mhm. Or 5 equals 9/5 B plus B.
Mm-hmm.
And now you want to get clever, right? So you
Yeah.
want to add these together. I'm sorry, you want to subtract this. It'd be nice if this is over 5, wouldn't it? Wouldn't it be?
It would.
What's 5 times 5?
25.
Over 5.
Mm-hmm.
That's how you do that.
All righty.
Minus 9/5 is equal to 16/5. So B is 16/5. I purposely wanted to have fractions in this. So that will go in for B.
Okay.
But the final equation is Y equals 3X plus B plus 16/5.
Okay.
If the professor wants you to put f of X, put f of X. Okay?
Okay.
That's what they want. Now
Right, they do.
let's get it in standard form.
Mm.
Right? Standard form, we need the Y, right?
Yes, we do.
You let the Y, then you bring 3X over. Right?
Mm-hmm.
You get minus 3X plus Y equals 16/5. Everything looks good except that. Do you remember what's wrong with this?
With this, I believe that
It's AX plus BY C, but what's wrong?
right.
All right. What's wrong with this is that A has to be greater than 0. This is A right here, right?
Mm-hmm.
And remember, B is here, it's 1, right? AX plus BY is C. So the way we make it equal to 0, greater than 0, is we multiply everything by -1. And we get 3X minus Y equals minus 16/5. Okay, let's do another one. So this would be standard form, right?
Right.
And this would be your MX plus B form, right? Okay.
Oh.
B is 16/5. All right.
Okay.
So standard form is AX plus BY equals C. So in this problem at the end, A is 3 now, that's fine.
Mm-hmm.
Remember, A can't be negative. That's all you gotta remember.
Okay.
A can never be negative. Okay?
Never. Okay.
That's one type of one we have to find the equation of line. Then they could do, you might review things like this. This is problem number 2. Let's say that point A is -3, -10. And point B is -6, -8. I put a lot of negatives on purpose.
Okay.
Okay?
Mm-hmm.
The question is, what is the equation of the line? Step 1 is find the slope. Now, in the first problem, it was given to me, right?
Mm-hmm.
So the second step is going to be right what I know. So what I got to do here is M equals Y2 minus Y1, if you will, over X2 minus X1. And what does this give me? I like the ones you have to be careful. Minus 10 minus a -8 over -3 minus a
-6. Oh, double negatives. Okay.
Yeah. So what's -10 plus 8?
-2.
-2. What's -3 plus 6?
3.
3. So the slope is -2/3.
Okay.
Okay?
Okay.
So it gets to be the same as we did before, right? Right, what you know.
Right.
Y equals, I'm gonna give you a couple, 1 or 2 to do for homework. Y equals -2/3 X plus B.
Okay, so that's our standard form.
No, that's
Well,
actually
not yet.
That's our slope form.
Okay.
Gotta get that first, unfortunately, the way I'm presenting the problems.
Right.
All right, so what do you do to find B?
We have to plug in, substitute the X and Y. We can choose from either one, right?
Right, which one would you like to use?
A.
Okay, doesn't really matter, they're both equally gnarly, huh? All right, so minus 10 is y equals minus 2/3 times minus 3, right?
Mm-hmm.
Plus b. All right, so we have minus 10. But look at
Mhm.
this. 3's cancel.
They
Minus
do.
1 times minus 2 is equal to, but minus times minus is positive, right?
Mm-hmm.
2 plus b, isn't that convenient?
Yes.
Or subtracting 2, what do we get for b?
We get -12.
Negative 12 equals b. So then we go back to here, right?
Yes.
Over here, the final equation is y equals minus 2/3 x minus 12. Now we want to go standard form. I love this problem for standard form
Mm-hmm.
because what? But let's just see what happens. Because a has to be greater than 0 is one problem.
It does.
That's definitely a problem.
Mm-hmm.
But we also cannot have fractions. A and b have to be integers.
Okay.
And I wonder, did we get that right the last problem? I bet. Yeah, we sure did.
Yeah.
It worked out. That problem worked out. All right.
Oh,
Did I lose my page? Oh, I'm right here, right? Okay.
yes, I can see.
All right, so now we got to add 2/3 to both sides, 2/3 x,
right.
to get it in standard form. Doing that, we get 2/3 x plus y equals, this is 0, minus 12. The only thing stopping standard form this time is right there. So how are we going to get rid of that? How do we get rid of the 3?
We can get rid of that by multiplying by 3 on both sides.
That's right. So 3, 3, 3. And we get 2x plus 3y is equal to minus 36.
Oh, Deacon Wilson, we have to apply the 3 to the y as well?
Yes, both sides. The whole side. You said it right. You said both sides.
Yeah.
Y is on the left side, isn't it?
Oh, okay.
Every term.
That makes sense.
If you don't hit every term, it's no longer equality, is it? As long as you do to one side, you do to the other side.
Okay.
Of the equal sign.
Okay.
So 2x plus 3y is minus 36.
Yep.
Standard form right here.
Okay.
I blocked over the other form right there. All right, now that's going to become important when you're computing that line for a reason I'm not telling you yet. In the calculus, it comes up quite a bit. In fact, you have to be able to do it quickly. That's why I'm showing you this method and not the y2 minus y1. You want a way to quickly be able to do it. And that actually comes up on the SAT too, believe it or not. All right, now that I've reviewed enough of linear functions, I now need to review, let's see, what is this class in, 10 o'clock?
10 o'clock.
What? What's the matter?
Oh, it's no problem. I don't have nothing to do.
It's actually 7:50. All right. So now I'm actually early. That's good. Now we're going to cover limits. Remember, Jessica and Corday are going to see this video, by the way.
Oh my goodness.
What's up, y'all? Anyway, let's take a look now at, I'm only going to cover the part of limits you need to know. So let me just throw some problems at you, and then we'll write a theorem down.
Okay.
Let's say we have f of x equals 3x squared plus 2x minus 2. And somebody says, take the limit of f of x. This is some good stuff, man. As x goes to 0.
Okay.
Okay? They say, what is that? Well, what it's going to be equal to is 3 times 0 squared, right? Plus 2 times 0 squared minus 2, or simply the answer is minus 2.
Okay, right.
So the limit of f of x as x goes to 0 of that function is minus 2.
Okay.
Let's do another one. let's say we have 1 over x cubed plus 2x squared plus 5 plus 5x. This is f. I should have put f of x in front, okay? Plus 5x plus 5.
Ooh,
You follow?
yes, sir.
What is the limit of f of x as x goes to 0? Well, let's figure it out. I don't want to have to write that down again, but limit of f of x goes to 0 is 1 over 0 plus 0 plus 5, right?
Right.
Plus 0 plus 5. Or 1 over 5 plus 5. And 5 is 25 over 5, somebody told you.
Right, right.
5 over 5, which gives us 26 over 5. So the limit of this function as x goes to 0 is 26 over 5. So what can we say about limits, this basic form of limit as x goes to 0? What do you actually do? What are the steps? Go ahead.
Plugging in back into the given equation.
And so in general, the limit, write this down.
Okay.
It's a theorem. Some professors like to prove it, but don't. If the teacher proves it, just go along with it.
Okay.
I'm not going to sit here and prove it. It can be. This can be proven, by the way. The
Okay.
limit as x goes to k, right, of f of x is simply f of k.
Right. All right. Yeah.
Makes sense?
That does, because k is what it's approaching, what x is approaching, and that's
Yes, sir.
Okay.
Now I know there's a whole lot more to it. Like sometimes you put in k and it's undefined. That's a whole, and you don't have to worry about that.
Yes.
That's not even. In fact, all that stuff you did on wholes and functions. But when I get to the mean value theorem, I'm just going to blow it away.
Okay.
It's just going to say as long as the point is differentiable, meaning that it's not a whole. So I don't know, I think this was all you need of limits to do calculus. Now I'm going to prove it to you.
Okay.
I'm going to prove it to you. All right. Any questions on this?
No, sir. All good.
So that's the setup. It's kind of like if you're watching Netflix, it's 10 episodes. This is kind of like 3/4 of the first episode.
Okay.
And now I give you the cliffhanger. We're going to do the cliffhanger and the solution in this session.
Okay. Okay.
See if this, I used to do this as 1 hour sessions. So this is right at the end of the hour, that'd be my cliffhanger. And then we'd end the session, but we're going to go a few more minutes. Okay. So let's go on here. This way works fine. And let's talk about nature and life now. Let's say we're looking at the progress of a runner.
Okay.
All right. Let's say this is distance, right? And this is time. So obviously over here doesn't exist, right? It's not part of the domain or the range or domain. Okay. So x less than 0 is not part of the domain.
Okay.
It's only x greater than 0. So let's say the runner of Walker, or the runner, goes 10 yards, and then the runner goes 20 yards, and at 20 yards, we're at 30 yards. And we could say, let's say he runs in a linear manner.
Okay.
Okay. And the time here was 1 second. The time here was 4 seconds, and then 7 seconds. So the time between these
Are
is,
3 seconds.
is the same,
Yes.
okay?
Mm-hmm.
Okay, I don't want to do this. Oh, what I didn't say is, okay, that's fine. So down here is where it starts, right?
Mm-hmm.
And what I want to say to you is, we can say that the runner ran in a linear manner. We could say that it was predictable and linear. In other words, and I wish I had done this right, but I didn't. Let's just say I do it this way. Let's say this is 2. I'm going to create the problem the way I want to.
Okay.
And let's say this up here is 3. 3 seconds to run 30 yards. That's probably right. I don't know. All right. So you can see that if he's running in a linear manner, he or she,
Mm-hmm.
in a linear manner,
Right.
20 minus 10, I'm sorry, that 4 minus 1 is 3. 20 minus 10, I'm sorry, 4 minus 0. Remember, ran from 0.
Mm-hmm.
Oh, no, it's 1 there. Let me think about this. Let me just start this a little differently and see. 20 over 4, 10 over 2, 10 over 1. What I'm trying to say is, let's
Mm-hmm.
suppose we have motion. Let me just go to new page. Scratch that page.
Okay.
Let's say these are the distances. Let's say this is the distances. These are the times.
Mm-hmm.
Okay. Well, I should say. Yeah, I'll put time on the x-axis.
Okay. Wait, isn't that how it normally is? Or I mean, it can be
Yeah,
either
yeah,
or.
it is.
Okay.
That was the matter of that's why my example wasn't very good. But this one is good.
Mm-hmm. Okay.
Let's say that after 1 second
Mm-hmm.
goes 10 yards.
Okay.
2 seconds, 20 yards. 3
Yes.
seconds, 30 yards. You can see that if you take 30 minus 20,
Mm-hmm.
10,
10, right?
the slope is always going to be 10
Okay.
all along this run here. If you went,
Mm-hmm.
say it was 4, it was 40. But the problem with life is that have you ever seen a race where the runners run the same speed the whole race?
Yes.
Really? Or do they go fast?
Very rare. Very rarely, though.
Wait, I'm sorry. On a 100-yard dash.
Oh, absolutely not.
They
No.
go faster and faster and faster and faster, right?
Right, right.
They have to. They
Mm-hmm.
actually accelerate, right?
Mm-hmm.
They run faster and faster and faster. So
Okay.
this is interesting.
Mm-hmm.
And the problems you did in algebra, like with cars and trains and everything,
Right.
but it's not going to work with over short distances and bursts. It's not going to work in space, because space, everything accelerates.
Mm-hmm.
It's not going to work. It can't explain nature. And in fact, historically, this was Galileo. Galileo realized right before he died, or was blinded actually, right before he was blinded, he realized that he was missing something, because he knew there were things in nature that sped up.
Right.
He knew it just by feeling the wind, and he knew it, but they
Mhm.
blinded him before he could figure it out.
Okay.
But then came along Isaac Newton. And Isaac Newton noticed they say from the apple falling out of the tree, we don't know, that things do speed up.
Mm-hmm.
It can go faster and faster. And he wondered, and he wrote a whole thing, Newton's 3 laws of motion. But then he had something strange he realized, Roderick. He realized, oh my God, things accelerate. Life isn't just linear. So the
Right.
linear model was not useful. But now we use things about it to understand the others. But he didn't do much more. Newton was big on forces. He knew forces move things. You know what he called the Principia. But he wondered, he called it the acceleration. He didn't see it that way. He called it something else that was accelerating. But then right about the same time they were studying Newton,
Mm-hmm.
there were other mathematicians in Europe that figured out that if we have a function,
Mm-hmm.
what they really wanted to know, what we really need to know, if you think about it, we really need to know is for any, like say a quadratic, one of them figured out for quadratic. Let's say for y equals x squared. Let's keep it simple. You might have seen this before.
Yes. Parent function.
So the question would be, if we're out here at 2, this is the point 2 comma 4, right? 2 squared. And we're at 3, it's 3 comma
3,
9.
9.
You
Mm-hmm.
can see it's not linear.
It's not.
I mean, in fact, if you go to 4, my God,
4, 16.
or 16.
Mm-hmm.
So if you just figure it out, I mean, 9 minus 4 is 5. 3 minus 2 is 1. That's 5. Then over here, 16 minus 9 is 7.
7
minus 3,
1.
minus 3 is 1. It seems to be getting a big, it's increasing. The
Absolutely.
rate is increasing. So then the thought was, what is happening right at this point? What is the rate of change at that point? Or listen to this,
Mm-hmm.
we can't really say because you need a second point. But
Yeah.
what if, Roderick, we take the point to be a tiny distance or
Mhm.
differential difference, a tiny distance to the right and left of that point? That's what we're going to consider on the next page.
Okay.
Because that would be a representation that's more realistic than saying everything's linear.
Right. Absolutely.
I mean, everything, it's funny, there's a regularity in this earth, like bacteria growth. You're going to find out later that the function called E. Right at the end of the course, I'll talk about y equals e to the x. We're going to talk about that.
Okay.
Been covered in pre-calc. But they began to notice that things are increasing. Now,
Mhm.
sometimes the increase rate was predictable, but it's increasing.
Right.
Okay. They needed a way to go to a certain point in time and figure out what was happening at that point. If you
Mhm.
ever watch, if you ever drive, if you drive yet?
Yes.
So you might have noticed already that there are
Mhm.
times you're driving along, everything's cool,
Right.
and then you speed up, and then you put off the gas, you slow down.
Right.
You realize that we could take a snapshot of your
Mhm.
speeding up. You might have been going 100 miles an hour over like 1 foot,
Yep.
and then you slow down back to the speed level because some kind of hazard might have been there, or you had to speed up and go around a ball,
Right.
or you wanted to pass someone. Something happened to make you speed up. So
Mm.
they realized they needed a way to measure what was happening at a particular time. And they figured it out with a thing called calculus. They figured out if they could move a small distance away from the point. Let me go to my next page. Oh, I did it in 15 pages. Usually it takes 15 pages. They realized, watch closely,
Okay.
they realized that for any function, I'm gonna say that's y equals f of x. That's a function.
Mhm.
That a point, I'm gonna call this point here. I'm gonna say there's a point here too. How's that? I'm gonna start with this point right here. At a given point B, because I want to call that A. At a given point B, you know what? Forget that. At a given point A, if we want to know what's happening at A, you can see it's beginning to increase, but you don't know how much.
Right.
You don't know how much. Well, one cool thing you could have done was shrink yourself down to the size of the atom, a really small superhero. What's that, Ant-Man? he couldn't go that small. Anyway, you go small as you can, or better looking at it, let's go an incremental distance to the right, left, and to the right of A. So small that this graph is too big or too far away.
Mm,
So what I'm gonna do is zoom in.
okay.
I'm gonna zoom in. And I'm gonna
Mhm.
move a small distance away to point B. And you're gonna get deja vu, something I showed you earlier. And I
Okay.
always put it on a separate, I always show this separately. So the point of this page was to tell you the problem with finding A was we need to get closer.
Right.
We need to bring B closer and
Mm,
take a measurement. Let's take a look. Calculus is, when you look at it that way, it's a little abstract. So here we are.
uh-huh.
It's our XY. Now watch this. Now I'm gonna blow it up.
All right.
This is gonna be point A.
Mm-hmm.
I want you to imagine that point B is an incremental distance away.
Okay.
In fact, if you've already drawn it, I want to make it further so I can make my point, okay?
Mm-hmm.
I'm gonna change page, but maybe you don't have to, I don't know. Oops, that's not a good one. I want to really have you see what I'm doing here. Oh yeah,
Mm-hmm.
be ahead of time, we doing good, man. Okay, here we go. Whoops. Oops. You should see these graphic tools I have here. Okay, here we go.
Okay.
It's a sad line, but let it be so. Okay. Suppose I want you to imagine that point B is a tiny distance away from A.
Okay.
Down here, so it goes over here. This is the Y values over here. The X values are down here. This point here, guess what?
Yes.
Is X1, F of X1.
Okay. Yes, that's what we just looked at.
You might be aware of that.
Mm-hmm.
This point here is going to be X2,
Two.
X2, comma,
Uh-huh.
F of X1 plus delta X.
Delta X
This distance here
is the change in X.
is the
It's the
change
delta
in
X.
X.
Mm-hmm.
This distance here is X1. That's X1.
Okay.
Now the whole thing is X2, right?
It is. Yes.
So F of X1, boom, takes you up to A. F of X2, boom, takes you up to B.
Mm-hmm.
All right, you ready? Here
I'm
we go.
ready.
You know, the problem is, even where they are, if you imagine they're close,
What was that?
they're too far away.
Okay.
We need to
Oh,
make delta X. We need to see what's happening as it approaches zero.
okay.
So let's write it out. The slope, if you will,
Okay.
seen this before, is F of X1 plus delta X minus F of X1 all over delta X. Okay?
Mm-hmm.
So the cool thing is that if you want to find if you want to get accuracy to what's happening at A, you got to make this distance, because still, no matter how far you can imagine it, there's a little curve.
Right.
And it's not really a straight line. But if we can get so close to A that the line going through A
Mm-hmm.
is a tangent line.
Okay.
meaning that the points are like right on top of each other.
Yeah.
They're closer and closer, but not touching. But they're right on top of each other. It's like 3.99999 and 4.
Right.
All intents and purposes, that's 4. It means that this M, the limit as delta x goes to 0 of f of x1 plus delta x right now,
Mm-hmm.
minus f of x1 as long as we let the delta x go to 0,
Yeah.
like we did in those examples, we
Right.
should be left with what we call dy dx, or you can say the change in y over the change in x at a given point, x equals xa. It's the change in y of the change in x. Look at all this terminology. So
Yeah, that's good.
let me write it out clean for you.
Mhm.
Again, it's you can see this as the
Mhm.
slopes used to do. The
Right.
problem with using that, you saw with that table, you're having a totally linear approach. You want to find out what it is at a given point, xa.
Right.
Then you have to let delta x approach 0. Be really close, asymptotically.
Mhm.
And the best way is taking the limit. So I'm gonna write it all out, and I'm gonna show all the notations in any book I've heard of for this. So here we go.
Okay.
The limit, I'm gonna write cleanly, as delta x goes to 0 of f of x1 plus delta x
Mm-hmm.
minus f of x1 all over delta x is referred to as the derivative
Mm.
of f of x, or y, if you will. So the derivative of f of x is the limit, I'm gonna say it 3 times, is the limit as delta x goes to 0 of f of x1 plus delta x minus f of x1 all over delta x. Now here's the cool thing.
Mm-hmm.
I'm not gonna say it 3 times. You can drop the x1 because it's true for any x value. You go a little bit to the right of it and you move the point to it. This is how you do it. So we could write it this way. We could say the limit, we should write it this way, of delta x, as delta x goes to 0, of f of x1 plus x1, I did it, f of x plus delta x minus f of x all over delta x is the derivative of f of x.
Okay.
What are some other ways of saying it? I slipped a minute ago, dy dx.
Okay.
What's another way of saying it? F prime of x. So, Deacon, why we have all these ways of saying it? I don't know.
Said this is what the books do.
The books do, they change all the time.
Absolutely. They do.
Also, I've seen it. Also, you'll see it the way I showed you the Riemann version. Delta y, this is the way they do it at UCLA, over delta x, evaluated at x equal xa.
Oh my goodness.
In other words, at a given point,
Mm-hmm.
you take the change in y over change in x, which is telling you you have to take a limit.
Wait,
yes.
I'm sorry. The last form that you just drew, the delta, you said the way UCLA does it, the delta y over delta x.
With the subscript x,
yeah.
X goes to x, x equals xa.
Oh, okay. Oh, xa. All right.
They're saying a given point.
Okay.
They hung up on remind you it's a given point.
Okay, the A is a subscript too, or is it?
Yeah, subscript 2.
Okay, all right.
Not yet. X sub A.
Okay.
Gotcha. What do you see most in school? This and this.
Okay. Okay. Thank goodness.
And you'll hear professors saying this. The teacher will say that.
Right.
The derivative of f of x. Now, Now that we have it, we need to test it.
Okay.
Let's test it on a linear function.
All right.
I better get M or it's invalid.
Mm-hmm.
If I use this and I don't get M,
Something's wrong.
that's invalid. I'm crazy. All right, let's do it.
Okay.
New page. Well, I'm using on page 20, buddy.
I'm gonna turn on the light.
Okay. It's getting dark, huh?
Mm-hmm.
All right.
I'm ready.
So let's say we have f of x equals 5x minus 4.
Okay.
I want to find f prime of x. Can I talk to you like that?
Yes, you can.
I'm gonna use all the terminologies on you.
All right.
And they all have different uses. So I'll find myself either in these 4 days explaining to you using these. F prime of x. Well, you say, Deacon, come on, man, it's 5. I know it. But we want to use our definition. And I every chance I get, I write it. I don't know why, man. You ready?
Mm-hmm.
I want you to be dreaming about it. As delta x goes to 0, of f of x plus delta x minus f of x all over delta x. That's how we get f prime of x.
Right.
So what do you step back,
Okay.
as we should do in calculus more often. You got to write down that first. Then you should write down that before you even start.
Okay.
Let's do it. I always say do that first. Don't start plugging in.
Okay.
So f of x plus delta x.
Mm-hmm.
See if you can follow me. Let's see how well you know your functional notations. You ready?
Yes.
It's 5 times
Mm-hmm.
x plus delta x minus 4.
Mm.
Shall I review it?
Yes, please.
All right. What's f of 2?
F2. Is it?
Let's say, what's f of 2? How do you figure that out?
Oh, plugging it into the for the x
5 times 2
Oh.
minus 4,
Mhm.
and you get 6, right?
Right.
What's f of 3?
It would be 15 minus 4. So 11.
All right, so what's f of triangle?
The triangle.
5 times triangle minus 4.
Okay.
The rule is whatever's in here goes in
Mhm.
for x.
Okay.
So f of x plus delta x minus 4 is
Mhm.
f of x plus delta x. What's f of x? What's f of x? Go back to your given. Look at your problem.
Okay.
What's f? Look at it right here. What's f of x?
F of x is
Obvious question.
you just
We just used it.
uh-huh.
What is it?
My goodness.
I love this about calculus. It's so
I feel like I'm
so
feeling so
obvious.
crazy right
So
now.
obvious. It's hard.
It's 5x minus 4, right?
Asking me or telling me.
I'm on the fence. I think. Wait.
Read what this line says right here. Read it.
Okay. Oh yes, 5x minus 4.
Right. You're gonna find yourself doing that a lot in an advanced class.
Okay.
That's because your mind is operating at a heavily analytical level, and a teacher just says, "What's 1 plus 1?" You can't do it. Plus, we're getting to about an hour of math. You start going crazy. That's why I moved to hands-on and not teaching. All right, so here it's just 5x minus 4. Right?
Okay. Yes,
so
sir.
So you know f of x plus delta x. You know f of x. We should be able to figure out f prime. Okay. You ready?
Yes. Go.
All right. So we go limit as delta x goes to 0 of 5 times. Remember, I don't do 2 steps at once. Have you noticed?
Mm-hmm.
Right there is f of x plus delta x. Number 1, yes?
Mm-hmm.
Minus what?
Minus 5x minus 4.
Look what I got to do. See me put that parenthesis in?
Mm-hmm. Yes.
Got to be careful. It's not minus 5x minus 4. It's the quantity.
Okay.
Got to be careful.
Whew.
Divided by delta x. Now we use a thing called distributive law. You might have heard of it. You might have heard of it.
Yes.
The limit as delta x goes to 0 of 5x plus 5 delta x, right? Minus 4, don't forget the minus 4.
Okay.
Minus 5x plus 4, yes?
Yes.
You see why it's plus 4, right?
Mm-hmm.
Minus a minus, all over delta x.
Okay.
Continuing, and notice how I keep writing the limit here, right?
Right, right.
Because that it's still that we haven't operated on it yet. We have to use that when we can, using what we learned earlier in the class. Limits delta x goes 0. Let's combine similar terms. What's 5x minus 5x?
0x. So
What's minus 4 plus 4?
0 again.
So I got 5 delta x,
delta x over delta
x.
And that's essentially
divide the delta x's, what do you get?
We get 5.
Which is what you expected. The slope is 5.
Right. So that was us testing to make sure that formula is equal to n.
Right. So it looks like it's a viable formula for linear functions.
Okay. Okay, Deacon Wilson, I think by one question
about
this, that makes sense.
Please.
But like, I don't know. I think I got really stumbled up at the part. How do I say this? I think it's the third to the last step where we distribute it at the top.
Let me number them.
Okay.
Which step?
Actually going back, actually at 1, where
so step 1, right?
Yes.
Step 1 is defining what f of x plus delta x is.
Yes. I'm so
It's just like here, you plug in x plus delta x for x.
Okay, so x is.
See, you've been doing it before, you just don't realize it. What did you do when you had f of g of x? That's why that was important when you were learning that. Let's say g of x is x plus 1. What's f of g of x? Well, it's 5 times x plus 1 minus 4.
Okay.
5 times x plus 1 plus 4. Because the x, see, this is what I want to tell you. I don't know how the teachers taught it. But if you have f of x equals 5x minus 4, amateur sees that. A pro sees this. A hole. And the question is, what goes in that hole?
Right. Okay.
So we say f of x plus delta x, and that's what goes in that hole.
Okay.
That goes in that hole.
Okay.
Which is really x2, but don't worry about it.
Oh my goodness.
It's not important.
Yeah. I think, I don't know.
Because it's all about A, not about B.
Right.
It's what's going on at A we care about.
I think just the 5 part kind of confused me. I feel like the 5 in step 1 was substituted for the F. I don't know.
No. I mean, f of x plus delta x is 5x plus delta x minus 4. Now, here's the thing. That means when you were doing these in school, let me go. I'm gonna come back to this page. So when you're saying things like g of x, your teachers, they just taught you to do it. They didn't tell you why you were doing it. What you're doing, listen closely, you're building a thing called composite functions. You're building a new function. When you say g of x is x squared, right? And f of x is 4x.
Mm-hmm.
F of g of x means anywhere I find x, I put g of x,
Mm-hmm.
right?
Yes, that makes sense.
So that means the f of g of x, you might have wrote it like this.
Mm-hmm.
I don't know if you wrote it like that. I don't know what people are doing.
Mm-hmm.
FOG, or do they do this? See, I like the OG way over here.
Yeah, me too.
But f of g of x is what?
Mm-hmm.
It's take f of x 4
Mhm.
times something is what it is.
Mm-hmm.
But what's the something? X squared.
Squared.
So it becomes 4x squared. What you have here at the end of the day, Roderick, is a
Mm-hmm.
composite
Mm.
of f and g.
Okay.
You've combined f and g like a hybrid.
Right.
And that's what's going on in that derivative problem.
Mm-hmm.
F of x plus delta x is a hybrid of f of x and x plus delta x.
Okay.
It's taking the rule we had, which is 4x, the other one was 5x minus 4. It's taking the rule and applying it to another function. In this case, x plus delta x.
Okay.
That's why the best question I asked on the other page was, what's
Mhm.
f? I asked you what's f of triangle. I should have used
Oh.
triangle. Let's do f of square. Forget about triangle. F of square is 5 square plus minus 4.
Mm-hmm.
All right, how about f of a triangle? It's 5 triangle minus 4.
5 triangle minus 4.
How
Mm-hmm.
about, watch this, this is on the last SAT.
Mm-hmm.
What's f of KET? So
5 KT minus 4.
that's it.
Okay.
So what's f of x plus delta x? Is the big question. Well, it's
Also, basically, we're doing 5 times. Okay, that was a very slow moment of me.
see it?
Yeah, that was okay.
Now, when you get this concept in class,
Mm-hmm.
everybody's going to stumble on it for several days. In fact, some people will never be able to do what we're getting ready to do in a moment with quadratics.
Okay.
Because my last problem I'm going to do, and I'm going to go a little over, is do what's the derivative of x squared?
Okay. Oh, man.
Now, the only problem is we don't have a way of knowing that I'm right or wrong until I tell you the power rule.
Right.
Now, let's go out. Let's do that one now. This is my cliffhanger.
Oh,
Here's my
man.
cliffhanger, like in Netflix. Let's say f of x
Mm-hmm.
equals x squared. The question is, what is dy dx?
Mm-hmm.
Now, do you like that? Say yes.
I'm kind of getting used to it. I'll say yes.
Same definition.
Yes, it is.
Let's do it. I always like to write it again. Sorry. Limit as delta x goes to 0
Mm-hmm.
of f of x plus delta x minus f of x all over delta x. After a while, you'll be able to write that fast, right? Because in my mind, I'm thinking about x that I'm moving an incremental distance away. What's that f? Then regular f of x and, subtract them. Sorry about that. All right, let's do it.
Okay.
Okay, it's good to know what f of x plus delta x is first. Let's do f of x first, so maybe you get that. What's f of x?
F of x, x squared.
Right. So f of x plus delta x is x plus delta x squared.
Okay.
You follow?
Yes, I follow.
Any questions?
Yeah, it's getting more better this time.
That's right. That's right.
I still get a little.
Because what we're going to do tomorrow, we're going to do cubed.
Okay.
And we're going to do 1 over x. And
yes.
then I'm going to say, wouldn't it be good if we had rules? Didn't have to do this all the time? And you're going to say, yeah, it'd be great. And I'll show you your rules. That's the way the course is going to go. All right, so then we'll show how to apply it. Okay, so here we go. This is a fun one, right? You got to watch, got to quality control me. So this is the limit as delta x goes to 0 of x plus delta x squared. Yes?
Yes.
minus x squared
Okay.
all over delta x.
Delta X. Mm-hmm.
Continue, limit. It's delta x goes to zero. I must be getting lazy. I didn't put an x in there. Equals, okay, how do you square this? Now we're going to square this the calculus student's way. You ready?
Yeah.
Square the first times the second and double it.
Mm-hmm.
Follow? It's
Mm-hmm.
just look, you can check on your own. First and second double, and then you square the last. I don't have to do FOIL. You notice that?
Wait.
You ain't
I'm
got
sorry.
time. You ain't got time. You ain't got time for FOIL, man. But what's x plus y squared?
Mm-hmm.
You want to do this, right?
You
You can.
I'm so used to looking at.
You can. First times
Okay.
first. Outer
Uh-huh.
times outer. XY. Integers of XY. 2xy. It's always
Okay.
twice the two numbers.
Right.
Squared. So all I did here was multiply them together, put a 2.
Okay.
Think about that. Okay.
Yeah.
This is a cliffhanger. Remember, we never get an explanation in the cliffhanger.
Oh man.
Divided by delta x.
Okay.
All right. Oh, I'm sorry. I'm tripping. That's the last term here. Minus x squared. Don't forget the minus x squared, right?
Mm-hmm.
All right, what's x squared minus x squared?
0.
All right, so I got the limit as delta x goes to 0 of, what am I left with? 2x delta x
Delta X plus delta X squared.
plus delta x squared all over delta x. If we divide each term by delta x,
Mm-hmm.
dividing this by delta x, they cancel.
They do.
X. If we divide this term, 2x delta x, by delta x, what do we get? 2x.
Right, because those two count. Mm-hmm.
All right, so we got 2x. What about delta x squared divided by delta x?
Mm. Mm. Oh, just delta X.
Delta x.
Mm-hmm.
So it's 2x plus delta x. And
Okay.
we're done. Well, let's
Yeah.
take the limit as delta x goes to 0. What does this become?
That becomes our
Make delta x 0. Come on.
delta X 0.
What are we left with?
We're left with just 2X, right?
You're asking me or telling me?
Telling.
So remember how we started the class off with the
Mhm.
definition of a limit? See why that was important?
Yes.
So the f dy dx is 2x
Mm-hmm.
squared.
Mm.
One more thing for you to think about. If it
Mhm.
was x cubed, you're going to find out it's 3x squared.
Okay.
What's
But my thing Deacon
my
was saying,
question tomorrow is going to be, how do those relate?
okay.
We're going to talk
But
about
Deacon was saying, how come delta X is 0?
because it's the
Oh, because
limit.
that's what it's approaching.
That's the definition.
Oh.
The limit of delta x, the limit as delta x goes to 0.
Mm-hmm.
But the end,
Okay.
the last step is to take it to 0, like we did in the last problem.
Mm-hmm.
The last step is to take delta x to 0.
Right. That's the goal. Okay. Okay, then.
So obviously we're gonna do more of this.
Okay. The 2X and the 3X squared. I'm trying to
So the
argue.
derivative of x squared is 2x.
The derivative of X squared is 2X.
Yeah, we just proved it.
Yeah. Yeah. What we just did.
We
Yeah.
used the definition.
Mm-hmm.
We
I was
proved it.
just trying to prepare myself to see how the 2X and the 3X squared.
Yeah, that's right. What happened? There's a rule being used here that we could apply here rather than doing all this.
Mm.
Look at the exponent. Where did it end up?
The exponent. Okay.
Of x squared. Where did it end up?
In front as the coefficient.
Where did the 3 end up?
Coefficient as well.
That's a clue. But why
Okay.
are you squared on one and first power on the other?
Mm-hmm.
I'm asking you.
Oh, for the first question. Oh, because it was
That-
linear. So it was just
So that's gonna be a clue to how we figure it out.
okay. No, that makes sense though.
So we're gonna do a few more problems using this definition.
Mm-hmm.
If you bad, assume f of x is x to the third power. What is f prime of x? Can you prove that it's 3x squared? That's the homework assignment.
Okay. Let me write that down.
Can you prove that it's 3x squared? If
Mm,
you do that definition of a derivative, you should get 3x squared.
okay. F
There's your challenge.
Okay, so I'm proving that what you just wrote, f of x equals x cubed. I'm
That's
proving that.
f prime of x.
Hmm?
You prove that f prime of x is 3x squared. I put a question mark. Is it?
Okay. Okay.
Prove it.
Yeah. Okay. Just through the work that we showed.
I want to like give you a way to know you're right. If you don't get 3x squared, you just some of your arithmetic was wrong. Or the way you placed your x plus delta x was wrong.
Okay.
Or maybe you multiplied out wrong.
Okay.
But tomorrow we'll do 1 over x. What's the derivative of 1 over x? So I have 1 over x plus delta x minus 1 over x all over delta x.
Okay. All right.
Okay,
Okay, Deacon Wilson.
I finished right on time.
Yes. Thank you, Deacon Wilson, for your time.
All right, I'll send you the video of the process.
Okay.
You have it for your posterity. I'll send it over to them too. All right.
Okay.
Thanks
See
much.
ya.
See you now. See you tomorrow, right?
Yes, tomorrow.
All night. Okay.
Same time, right?
Same time, no Saturday, middle of the day.
Yes. Okay. Gotcha.
All right, we'll see you.
Later.
Bye-bye.